London forces, or London dispersion forces, or dispersion forces, or van der Waals interactions, all of these same terms mean the same thing, are interactions that occur in compounds that are nonpolar. They can occur in polar compounds too, but they'll occur in nonpolar compounds when there is just a random movement of electron density within a compound. So this is a picture I've tried to draw here of a compound that has 1, 2, 3, 4, 5, 6, 7, 8 carbons. All right. Now I haven't drawn the hydrogens on there for simplicity. And this is just kind of a way to help people understand how London forces work. But we could say this is octane, right? Octane is a chemical, C8H18, which is in high abundance in gasoline, automotive gasoline, right? So if each one of these gray small spheres here represents the nucleus, and if this purple sphere, if these purple circles here represent the electron density, all right, you can imagine the electrons zooming around, and this down below here also represents the same thing up here. Each one of these red and blue clusters here represents a nucleus, and the moving electron around the nucleus represents the electron density kind of going around. We could also kind of represent it this way, where the electron density on an atom or on a molecule is constantly in fluctuation. And at any one given moment in time, if you were to freeze the electron density on this molecule up here, you would find different regions of electron density, right? Different regions of the molecule that are different in terms of their electron density. So here, we could say right now, the way I've frozen this molecule, is there's not a lot of electron density. But over here, you can see that there's extra electron density. A lot of electron density over here, maybe not so much right in this area right there, right? Now, that just happens to be how the molecule stopped when I stopped at that time, right? I can let them spin again, and I can stop it again and say, oh, there, when I stopped at that time, this side of the molecule happens to have a lot of electron density, and this side happens to not have much electron density. So you have these dipoles that are developing. They're not long-term dipoles. They're just kind of, as the motion and the flow of the electron density goes, there will be certain times when there's what we call an induced dipole, or an instantaneous dipole. Okay? And when this instantaneous dipole occurs around a neighboring molecule, then you have a chance of having these types of dispersion forces, or London forces. Okay? So, for example, here I have two molecules that are next to each other, right? Is there an attraction between these two molecules? Well, these are chains of carbons, so there's no dipole-dipole. It's not. These are non-polar compounds. There's no dipole-dipole. There's definitely no hydrogen bonding, right? But there can be these London forces, because if I stop the molecules, let's see if I get lucky, I'm going to stop them right here. I stopped them right there, and right here you see in this molecule right now, there's a little lack of electron density right here, but this molecule is kind of pushing its electron density towards that region. And so you'd have an instantaneous dipole, a moment there where there would be a stickiness between these two molecules because of the electron density moving from one and kind of being attracted by the opposite, or a different molecule here has a opposite charge exposed. All right? And I call this the London Dispersion Forces slot machine. So we'll play it again. Ready? Here we go. Let's see if we get lucky. 1, 2, 3. Oh, what do you think, Camille? Does it look like I got lucky here? You there, Camille? What's that? Say that again?
No, I don't think.
I didn't find any regions where one was kind of leaning its electron density in and the other one was withdrawing its electron density at the same time, right?
Yeah.
Okay, so let's try again. All right, let's try again. Stop. Ooh, oh, maybe. Where do you see, Camille? Any spots here where it looks like I might have gotten a little bit of interaction between these compounds?
Maybe on the top one.
This one here?
Yeah.
Which one? Which one? Well, this one, I'm not seeing where this one is reaching towards this molecule. But see this one right here, how it's kind of exposed a little bit?
Oh, yes, I see that. Or like the, okay.
See, this one would be a partial what? What kind of charge would be exposed here?
Positive?
Yeah, partial positive, because there's not electron density here. But this top one has some electron density kind of coming down towards this area a little bit. Can you see that?
Yes.
Okay. Let's try one more time because it's just so darn fun. Let's see if we can get another one. What do you think? Anything, Camille?
In the same exact one, there's very, very, very little.
Oh, here being a little exposed a little bit, and there's a little bit over there? Possibly. Yes. How about this one? There's a little bit of exposure here, and this one's kind of reaching into that space.
Yeah, just a little bit.
You know what we can do? You know what we need to do is we need to make a better slot machine with more chances, right? If I have a really long molecule, and I see, so here I have two molecules that are really long, and here I have two that are really short. If I play the slot machine with a really long molecule, how does that change my my chances, Landon? Yeah, I get more chances, right? I get more chances. I get more chances because there's just more motion and there's a higher chance that at some point here, let me just stop it here and find out. Oops, there we go. Stop it there. Doesn't look like much over here, but over here it looks pretty good, right? Some electron density reaching down towards this atom there. Can you see that? Let's try one more time here. Ooh, not much of anything looking good there. Maybe here a little bit. Ooh, still not good. All right, let's do the small one now. When I do the small one, Jace, do I improve my chances or decrease my chances of having some London forces here, Jace?
I feel like decrease your chances.
Yeah, I don't have very much of a chance, right? Because I just have three atoms in these molecules, and so the electron density doesn't have a very large chance. And so the result of all this is what we call, what we see is an increased, where are we at? Where are we at? Increased boiling point. Is that the table I want? No, that's not the table I want. Well, I gotta find it here. Let me find a good table here. It changes, or it shows us that there's a increased boiling point of different molecules that are non-polar, but just differ in their size. Let's see. So I'm looking for the boiling point of different hydrocarbons. Okay, so here I have a list of different boiling points for these different hydrocarbons, right? So here's methane. That's just one carbon. One carbon has a boiling point, let's look at those, at negative 164 degrees Celsius. So to get it to become a liquid, you have to get the temperature down to negative 165 degrees Celsius. Ethane, that's two carbons, right? My boiling point increases. And I can get a higher and higher boiling point as I get more and more carbons These are not polar compounds, but yet the boiling point does change. In fact, here it is, octane, boiling point of 125 degrees Celsius, right? So you have to raise the temperature a lot of octane to boil it, right? These are gaseous at room temperatures. These are liquid. I can even get 30 carbons being a solid at room temperature, right? So why do we see this trend of increasing boiling point as we increase the number of carbons, Harry? Why is there this increase in boiling point as we see an increase in the number of carbons in a molecule?
Is it because the more carbons there are, the higher chance there is for a London dispersion force to occur?
That's right. That's right. We have more carbons. We have a higher likelihood of having London forces holding those molecules together. Now, London forces are predominantly talked about, considered when you're thinking about nonpolar molecules, because if you have a dipole, a molecule that has a dipole, it's going to form dipole-dipole interactions, yep. And those kinds of interactions are going to be generally stronger than an individual London dispersion force. However, if you have a really big compound and lots of little London dispersion forces, can actually be more influential than a single dipole. Okay. All right. So another thing that plays account, or it needs to be taken into account, is the shape of the compound. So this compound here is pentane, and this compound here is also pentane. All right. So pentane. Any ideas, Brielle? How many carbons do you think are in an atom of pentane, or a molecule of pentane? You know what pent means?
5.
Yeah, that's right. So let me draw the one on the right here. Draw it out for us. 5 carbons. 1, 2, 3, 4, 5. Whereas neopentane over here on the left, same chemical formula, but it looks like this. Carbon, 2, 3, 4, 5. All right. Now, when one of these neopentanes comes in contact with a neighboring neopentane, right, and it tries to form intermolecular interactions, all it has is London forces. These are nonpolar compounds. But what do you think, Brielle? Which one of these is going to have a higher probability of having London forces between them?
The longer atom chains, so the ones on the right, other than the compact,
That's right.
will have sides. Yeah.
Yeah. More likelihood of having interactions here because they're spread out, right? Same chemical formula, C5H12, right? But with the longer the chain being spread out longer, we get a boiling point shift from 9.5 to 36 degrees Celsius. Okay, so shape plays a role as well. All right, so we've introduced now dipole-dipole interactions. We've introduced hydrogen bonding. Now, hydrogen bonding is just a special kind of what interaction, Sarah? Hydrogen bonding is a special kind of what?
Dipole-dipole interaction.
That's right. It's a special kind of dipole-dipole interaction in which what sets it above and beyond a dipole-dipole interaction, Sarah? Why?
I know it has hydrogens bonded to fluorine, nitrogen, or oxygen.
Very good, very good. And so those dipoles are really strong dipoles, right? Because hydrogen can't even maintain much electron density compared to nitrogen, oxygen, or fluorine. It gives it all up, basically. So you have really strong dipoles. And you can result in very strong dipole-dipole interactions, which we call hydrogen bonding. So we have our dipole-dipole. We have our hydrogen bonding, which is an extra strong dipole-dipole. And then we have London forces or dispersion forces or van der Waals interactions, which is another name that you might see on an exam. Okay, very good. Then we can also have what we call a dipole-ion interaction, and we briefly discussed this previously. But here is a water molecule. And what is this positively charged thing right here, Camille? What is that trying to represent?
Ion.
It's an ion. That's right, an ion. For example, sodium chloride, right? NaCl is a compound of sodium ions and chloride ions. And when water gets next to sodium chloride, salt, the sodium chloride molecules, let me see here.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium.
Let me put it on mute there. You guys have seen this video before though, right? Sodium chloride goes into water. Sodium chloride is an ionic compound, three-dimensional lattice. The water molecules there, right? They bond to the ions and pull those ions from the three-dimensional lattice away, right? I think I've shown this to you. Hope I've shown it to you a couple times already, so that you have a good idea of what happens when you take a salt and dissolve it in water, right? But now we have a name for this kind of interaction, right? The interaction between, for example, water and an ion, either a positively charged ion, and in this case the oxygen is going to lead with that interaction because it has the negative side of the dipole, or the hydrogens are going to lead in the interaction with a negatively charged ion, right? Okay, so Camille, what do we call this kind of interaction between ions and water molecules? What are we going to call that kind of interaction? Is that a dipole-dipole interaction? Is that a hydrogen bonding interaction? Did your microphone stop working, Camille? It's called an ion dipole. Very good. She wrote it on there for us. Excellent. That's an ion and a dipole interacting with each other. Very good. Now, I think that is a good place to stop for the day. So,